Hi class, welcome to our GradStats 2024 Lab series. In Lab 4 for R and RStudio, we're doing multiple and hierarchical regressions and model level assumptions. So multiple regression is a statistical analysis technique that builds from correlation, but it enables us to look at relationships between multiple variables. And this is more realistic to the real world questions we have in organizations and in practices. In this lab, we're going to conduct and interpret a multiple regression and a hierarchical regression. We're also going to evaluate the quality of the model, of the regression model, by performing model level assumption checks. So, materials you're going to need here are the dataset survey.sav from Pallant's SPSS survival guide, the Lab4 R script, and the starter tables Excel. So go ahead and download those things, get them into the working directories and the folders where you know your stuff is at, and we will get started. So in RStudio, we're going to start opening our information and getting our environment populated here. We'll start by getting our Lab4 script and the goals: conducting a multiple regression, evaluating the assumptions, and conducting a hierarchical regression, which is a little more complicated. We have more results that we need to report when we're starting to do models that we're comparing, and getting everything together for our write-up, getting our prediction equation, and creating a table. So lots to do here. Your prep, you need to have the dataset survey.sav, and the packages we're going to be using are these: Tidyverse, Haven, LMBeta, MBES, Broom, and Core. So a different way that I wanted to show you guys for working with getting your packages ready is over here in the files, plots, packages, the kind of everything else area. If we go to packages, anything that you've already installed on this computer that you're working on is going to be here in this list. So I can go down to Tidyverse, it's alphabetical order. I can go down to Tidyverse right there. It's already installed, that's why it's on this list. And I can just check this box and that will run the library function. So it's a different way that you can load a package that's already installed. So let me go get Haven, LMBeta, MBES, right there, Broom, and Core. So there's Core and Broom. So here I don't have Broom, right? That means it has not been installed on this computer. That's no problem. You can go to this install icon and type in the name of the package. Selecting that, install, and it'll do that install packages part, right? And now that it's in my list, I can just click and that runs library. So it's just a different way to get your packages ready using the packages tab over here that I wanted to show you. Okay, so everything's ready to roll. I want to read in the survey data set, and that's why we wanted the Haven package, because we're going to read in a SAV file. We're doing survey.sav. So I'm going to go to import dataset and from SPSS. Brings my little dialog box here, and I browse to the survey.sav dataset. Creates a data preview, and here, when we're importing a SAV file, we don't have the ability to change the nature of the type of variables that are coming in here. When we're importing a different type of file, like a tab delimited or comma separated, we can change right here in the dialog box the nature of a variable, but not when we're using SAV. But no problem, I'm going to leave the name as survey, just because that's how I created the script this time, but you can create whatever name you want to make it easier to type. And import. So now it's in my data, in my environment. Went ahead and did a little view here, and we can see that it thinks the ID character is numerical, which I'll have to fix. So in our lab, we have 439 observations of 130 variables. So good to know. We do want to set that ID to character. And this is where like really making good script helps you, because you can go back to where we set ID as character before, copy that script and bring it over to your new Lab4 script and be able to just adjust according to the name of the data set and whatever the name of the ID variable is. So I'm going to type this in real quick. Or copy paste it from my other script. So survey ID is going to be assigned by this function, make it a character on what? On the variable ID in the survey data set. So now my ID is a character type. Cool. I'm not going to worry about the factors because I'm not using them in this lab, so I'm not going to do all that, but you could just the same thing, copy your script from a prior script there where you created all of those factors and just copy it into this new lab. Next, I want to reduce to just our lab variables, because there's like 130 variables is a lot, and I only need 6 of them. So I'm going to select just the ones I need here. This time I'm going to give it a new name too. Instead of survey, I'm going to call it survey1 so that I don't overwrite the original in case I need to go back to it. So these are the variables of interest we're going to be working with. Here, this is just say select from the dataset survey or from the environment object survey these variables. I'm retaining the ID. I'm keeping age and social desirability because that's going to be part of our hierarchical regression. And then I'm keeping total mastery and TP COAS, which are my predictors, and my outcome of TP stress. And those are the only variables that are going into my models. So those, I'm kind of getting it more clean so that I can just work with the ones that I need. Now another thing we're going to do here, missing values in our target variables. If we have values missing like in mastery, but then not missing in stress, it still can't use that case because it needs all of its variables to be able to work. So we're going to use a new function. It's called tidyr, but it's already part of tidyverse, so we don't have to load up a new package. We already did that when we loaded tidyverse. So the way it looks is like this. I'm also going to make a new data set called survey.2 again, so that if I need to go back to the one that I did not drop variables for, I can. It's just right there. So I'm doing reiterations or new versions so that I don't lose information that I might want. Nope. Have to remember the pipe again. Nope. Shift Control M. I do this every time. I have to remember what my shortcut is for the pipe. I should probably put it on a sticky note so I see it. So what we're looking at here, we're using the function drop missing values in these variables. So if they're missing any values for a case, the case would be dropped. And we started with 439 observations, but once we run this, okay, I have an error. It says it could not find the function drop.na. So let me see what's going on here, because it did not put my item over there. Plus I still need survey 1 over there. There we go. I forgot to run that. So here it says that it can't find drop NA. Let me go back and check it out. Like I said, this is part of the tidyr package. I can double check and make sure tidyr is in here. Yep, it's in my packages list. It's already checked. So it shouldn't be a problem with the package. So when I click on the link here in the packages area, it opens up that package in the help files. And I can scroll down. I'm looking for drop NA because that's the one it says that it's not finding. So scrolling down, oh, there we go. Drop underscore NA. Oops, I put drop period NA, so I mistyped that. Let me put drop underscore and see if that works. Okay, now it's happier. So I have my original, I have when I pulled in just the 6 variables like I selected up here, and then here I'm still having the 6 variables, but it dropped the ones that had missing values, dropped any cases that had missing values. And you see now we're down to 423 observations of those 6 variables. Cool. So moving forward, in your preliminary work, you're going to do a general description of the data set and variables of interest. And our variables of interest, like we said, are those that are going to be running in the models, like age, T-Marlow, T-Mast, total perceived stress, and TP-COAS. That preliminary assumption checking that we were doing before, like checking univariate normality of our predictor and criterion variables, you still do that with your histogram and your checking Shapiro-Wilks. And your bivariate linearity is between each predictor criterion pair. What do I mean by that? Well, our research question is, how well do 2 predictors, total mastery and perceived control of internal states, predict perceived stress? So perceived stress is the criterion, the outcome. And we have 2 predictors, mastery and perceived control. So when we're looking at bivariate linearity, we want to know mastery and stress, and we also want to know perceived control and stress, right? So we need to check out bivariate linearity twice. Once for each of predictor with the outcome and predictor 2 with the outcome. So those are your bivariate linearity checks, again with your scatter plot and your correlation test. And typically when you get that general description of the data set, you call for a correlation table between all the study variables, and usually you have all the correlation tests right there. So we're going to move on with the multiple regression itself. And what we need to do is tell R that we want a linear model of perceived stress predicted by mastery and perceived control of internal states. We're going to create this linear model and we're going to save it into the environment. So I chose the name Multiple Regression 1, MR1, assigned by, and here we're going to want linear model of what is the outcome? Total perceived stress predicted by, that's the little tilde above the tab, total mastery and total PCOS. Okay, and I'm definitely missing, I believe it's a plus here. I'll double check my prior script. And we need to tell it what data set it's pulling from. Yep, we got a plus, and then after it, we do a comma, and we tell it what the data, where the data are. Survey.2. So linear model, total perceived stress predicted by total mastery and total perceived control, comma, use the data called survey.2, and that has to be in the environment for it to know what you're talking about. So we run that, and now we have MR1 in our environment. And we can go ahead and get the summary of that. MR1. Oops, forgot to hold my command key down. And that gives us the information about the model and the coefficients, all of that. But I know I'm going to need the betas anyway. So I'm going to go ahead and run and make a new item called MR1 beta where I can get the standardized regression coefficients. So run LM beta on the regression MR1 that's already in the environment and give me a summary of that guy. Oops, there we go. It had the red thing because I was still writing, but I kind of just already ran it and then it figured it out that it was okay. So let's take a look at this output here. We have to describe the model. What are the results of the model? And once we have all of that information, we go into some details on what are the results of the specific regression coefficients, those predictors. So when we're looking at the results of the model, we're looking at our F line, that we have an F stat of 182.4. The degrees of freedom are 2 and 420. Now, I did notice there's just little slight rounding differences between SPSS and R, like the 182.4, it's a little different, but no worries, it's still a significant model. That did not change between SPSS and R. It's still pretty close, right? This p-value is definitely less than p less than 0.001 because with a -16 here in scientific notation, that's like 15 zeros, like decimal, 15 zeros, then 2. That's a lot less than 0.001. So anytime you see like a negative scientific notation indicator there, it's less than 0.001. Our R squared, our effect size for the model is 4649, which says 46.5. If I convert that to a percent and go to the tenths place, 46.5% of the variation in total perceived stress, that's the outcome, is explained by the whole model, not just one predictor or another. The whole model explains 46.5% of the variation in total perceived stress. So that's the information, most of the information we need for the model. We still need the confidence interval, which we'll get next, and then we'll look at these coefficients. Let's see. Okay, I went ahead and gave you the information for coefficients here before we called for a CI. So let's look at the coefficients. Here, mastery has a -0.61766, so 0.62 decrease, that's that negative, in total perceived stress. So for each 1 unit increase in mastery, we have a decrease in total perceived stress at 0.62. And then, and this is a significant predictor, and we have the beta, the standardized regression coefficient for it, whereas the estimate here is the unstandardized regression coefficient. So when we're explaining to an audience about what is the impact here. For every 1 unit increase in the predictor, we have this much predicted difference happening in the outcome. It's a different conversation for the standardized ones. So let's look at TP-COAS. We see that it's a significant predictor, and its estimate unstandardized regression coefficient is negative 0.18. So for every 1 unit increase in total perception of control, we have a decrease in total perception of stress of 0.18. And again, are standardized. So what the standardized effect size gives us is relative comparison. In this one model, comparing between these two predictors, so it's very relative to just this model, we can see that total mastery has a stronger impact than perceptions of control. And that's something that we can also explain to our reader, that when it comes down to it, having control of external events seems to have more impact on reducing perceived stress than our perception of internal control. So it's some information that sometimes you can use for decision making. Now, explaining exactly how these numbers relate is a little more difficult for your audience to understand. So what's going on here with a standardized effect size is that now it's based on standard deviation. For every 1 unit change in the standard deviation of mastery, we would have a decrease of 0.41 standard deviations in total perceived stress. Yeah, it's like I would have to draw that picture a few times before I could actually explain it to someone in a way that they could understand. So when we're talking to an audience about the impact, 1 unit change here has this much change there, that is much easier for your reader or your audience to understand when you're talking 1 unit change in the predictor. But if you're talking about when it comes down to relative impact between these predictors, we can say that mastery is a stronger predictor, and you're getting that from your standardized coefficients. So something to be able to go back and forth on when you're trying to interpret. Okay, we still need the CI for R squared, and what we want there is our CI formula. I'm looking back to see if it says it dropped any values here to know what my accurate N is. But remember how in the beginning we made sure all the variables that had any missing cases, we dropped cases with missing variables. That's why there's no indicator here about we dropped so many. So in survey 2, we have 423. Now we have our confidence interval from 39 to 53. Cool. That's the information we need for reporting the results on that model, the results of the model run, the linear regression, and the coefficients. But we still need to look at the model level assumption checks to know if there's any violations of assumptions that could be impacting an accurate interpretation of the results. So one thing we want to know, are the predictors highly correlated? This is called multicollinearity. Now, had we run a full correlation table in our preliminary work, we would already have these numbers, all the correlations between the study variables. But we can also just ask R for the correlation between two variables. Alrighty, this is saying give me a correlation test using dataset survey2 variable. That's what your $sign does, is say, okay, the next thing is a variable within that dataset, variable tmast, with, correlated with, survey2 TP-COAS. And in here, we got a lot of great information. We have, maybe you didn't even realize that correlations also have a degree of freedom, but we don't usually report it. Our p-value is significant. There's a significant correlation between these two. And it even gives us the confidence interval of the correlation estimate. Kind of cool. I don't usually report the confidence interval for that. I usually, when I'm doing a correlation test period, I usually report the correlation coefficient, the significance, and the R squared, the coefficient of determination. For our purpose here, looking at multicollinearity, we just want to know what this number is. It's a 0.53, which means it's less than 0.9. So we only have to worry about multicollinearity between the predictors when the correlation is greater than 0.9, and it's not. It's okay that it's significant. It's not okay if it's above 0.9. So we can tell the reader, no problem with multicollinearity here. For singularity, this is saying something about our data. We need to know what variables are predictors and if there's any items in the predictors that are being counted more than once. Like all of those items that we use to create the scale score for total mastery, we don't want to use the total mastery score and some items for mastery as well, because then we're counting them twice. We have them in the model for items and for total mastery, and that is a violation of singularity. You would also see the situation if any items in mastery were also used to create total perceived control of internal states. So again, if you have any items that are in the model more than once, it's a violation of singularity. So we're not really running a test here. We're just knowing how our data are constructed. And then we have a couple more steps to gather those other regression diagnostics infos. And this is where you need that Broom package. We're going to use the augment function on the linear model to get those residual information that we need to check out the characteristics of the residuals. So we're going to now we have the multiple regression 1 regression diagnostics. It's just the name I gave it. You can name it whatever you want. And to get a summary of that, we'll just ask for a summary. Okay, let's see what we got here. We have our 3 variables that are in the model, and then we have these ones that we haven't seen before. Dot fitted, dot resid, dot hat, dot sigma, dot cooksd, dot standard resid. So let's look at this a little prettier. We'll do view and put it into our into a prettier table. Here we go. So stress, mastery, TP-COAS, fitted, resid, hat, sigma, cooksd, standard resid. Cool. So what's going on here? Recall that we have residuals. What are they? They are the difference between the actual value from the participant and what we expected it to be. So if I'm looking at the resid for total perceived stress, and here's what total perceived stress actually was, then the difference is, so I've predicted it was 28.26611, and the residual for it is 0.73389,374, right? So here, the difference between what I predicted and what it actually was is the residual. And we can check it out with the calculator. We can just say, okay, take my 29 minus the fitted. $73389. So we want to know the characteristics of these errors, of these error terms, and that's what our assumption checks are mostly about. So here's what we just talked about. Fitted are the unstandardized predicted values, and this is similar to what you saw as pre_1 in SPSS. Resid is the unstandardized residuals. This is the one that's called Res1 in SPSS. And then Cook's D is the one that was called COO_1 in SPSS. And that's the one that tells us if a specific case is having undue influence on the regression, in other words, an outlier. So looking at outliers, we want to look and see if Cook's distance is greater than 1, because that would indicate a potential issue. So when we go to our table in the view, we're going to sort Cook's D using the little arrows right there. We have, that's a very small number because it's to the -0.9 scientific notation. So I'm going to hit it again and sort descending. So the largest Cook's D is 0.095, or if you round 0.96. Even if you round the 10th place, it's 0.1. But our cutoff is 1. So we're nowhere near a whole 1. So what do you think? Like, put your perspective in here on looking at the outliers by evaluating Cook's D. It looks like we're nowhere near 1, so I'm not going to worry about it. The other areas that we're looking at are normality of residuals, linearity of residuals, and homoscedasticity of residuals. And when we're talking normality, again, the things that we do to check out normality are the histogram and the Shapiro-Wilks. We're just going to run that again because we have a variable now for residuals. Right in here, there's our residuals. So we're just running the same type of information that we asked before for histogram and for Shapiro-Wilks. This is what it looks like. I want a ggplot. My data are the M1 regression diagnostics. And then I want to ask for a histogram. And on the x-axis, I want that dot resid. So let's take a look at the histogram. And this is a histogram of the residuals. So the error terms in the model, they're not about TP stress, they're not about mastery or perceptions of control. These are the error terms in the model itself. So after we explained total perceived stress, what was left over? And looking at this, does this look normally distributed? If we imagined a normal curve over it, I think you can even add a normal curve in the histogram call. That would be a cool thing to check out with the AI stuff. Just give it that line and say that you want to add a normal curve overlay, and the AI might be able to find it faster than you can find it with a Google search. And then a Shapiro test, again, is the test of normality. Running that. So I am less than 0.01 there, 0.05 there, which is a significant test. So according to Shapiro-Wilk, our residuals violated the assumption of normality. And you can go either way with that. You can say, hey, it looks like I have a pretty normal curve, but it does violate Shapiro-Wilks. Or you can say, oh, that looks a little peaky. Don't think that's very normally distributed. And it's confirmed with a significant Shapiro-Wilks test. Therefore, I'm going to call foul here. I'm going to say that this model seems to violate normality of residuals, so we want to be careful in our interpretation of its effects. So you just want to use that tentative language. Again, we're never proving anything. We're saying, hey, here's the likelihood, here's what we think would be predicted from the data that we have, right? And we only have a sample. We don't have the whole population. So that's normality of residuals. Linearity of residuals. Now we're looking at, is there a relationship? And the way we evaluate relationship visually with a scatter plot between two continuous variables, right? And the way we test a relationship is with a correlation test. So what is this big deal? Why do we want no relationship between the residuals and the predicted values? Well, it goes to, if my predictors are explaining all this variation in the outcome, then if the residuals, the error terms, are related somehow to the predicted, then it means someplace there's another predictor that I haven't accounted for here that should have already been explained in T-mastery or TP-COAS. So residuals are just the error terms that are not supposed to be related at all to what we already have in the predicted. If there was a relationship, there's something wrong. There's a predictor missing. So we're looking for no relationship when we're looking at these. So first, we want this scatter plot. Again, you can go back and copy your ggplot work or any place where you've already done a scatter plot, and then just update the information. Let R know what data set you're really using now and what the X and Y values would be. So we put the predicted on the X-axis and the residuals on the Y-axis. So let's take a look at that scatter plot first. So just looking it through, do we see an upward or downward trend here between the residuals and the predicted values? Not really. They're all over the place. And again, if we know we want a correlation test between A and B, we can just tell R, give me a correlation test. Here's my first variable from the multiple regression dialog item in the environment, and here's the variable, and then same thing with the other variable. Okay, we have our information. We have that the correlation is lots of zeros and then 3578722, right? So lots of zeros, 15 zeros after that decimal place. That's pretty much a zero correlation. You'll see that the p-value is 1. Like, it's so much non-correlated that the p-value actually exceeded 0.9 or whatever. So we can say with confidence that there is no relationship between the fitted and residuals information. So we do not violate linearity of residuals. We're good there. Okay, homoscedasticity of residuals. And that's that spread of information across the predicted values. Do we have kind of the same amount of spread going on across these? I'm not seeing a whole lot of problem here. And it's just a visual inspection either of this scatter plot between predicted and residuals, but we also have some other ways of pulling our regression plots. So here I asked for a plot of the original regression, so MR1. And when I command return this, now we got to go to the console. So down here, we just ran it, and it says hit return to see next plot. So I'm putting my cursor right after that, and I'm hitting return, and it's going to change the plot in the plot area here. So now, here's the residuals to fitted, which is the one we just ran, that scatter plot, but they put this nice little line to show us the midline, that 0 line, so that we can look and see, okay, how's the spread going above and below this stuff? And they have 3 more plots here. I'll hit return again. Here's our QQ, which is similar to the PP plot in SPSS. And we have our expected, like that diagonal dashed line is the expected path of the residuals, whereas the dots themselves are where the residuals landed. And they even marked out some that they considered outliers here. Then let's do one more plot. Scale and location. So this is fitted values to standardized residuals. It's very similar to the prior one. You're looking at spread between the fitted values and the standardized residuals. And then one more, but we don't use this one as much, is, so this is not the square root. This is residuals versus leverage. And we haven't really talked about leverage, so we don't use this graph as much. Leverage refers to when an outlier, when a particular case is pulling the regression to a certain side or another. So it's recognizing some leverage issues there, but we're not going to look at that one this term. So we can go through our plots here, and if there's any that we want to keep, we can export the plot to keep for a write-up. Okay, so that is all the information we have. You would pull from your data, from your items, your console, and to be able to get the information that you need for write-up. And it's pretty much the same write-up as the one we have on our lab sheet for SPSS. Like I said, there are slight little differences. Let me go back to the multiple regression write-up. Like here in SPSS, we had 186.49, but in our, let's do summary of MR1, oops, where the F value is 182.4. So going back 186.4 or 0.5 and 182.4. A little different, but the p-value is the same for both of these. And let's look at the multiple r squared. 0.465 and this one's 466. Very little difference, 39 to 53, and that's what we got on our confidence interval as well. So not worried about it. I think it's something to do with how each of the two systems is dropping the cases that have missing values. So cool, it's fine. Then we're going to, what do we have next here? Hierarchical regression. This might be a good place for a break if you want to take a little stop and be able to kind of shake it off before we go into hierarchical regression. So, hierarchical regression. If we were to control statistically for some effects of predictors that we can't control in our design, would our predictors, the ones that we're really interested in, still be able to predict perceived stress? Specifically, I can't control the age of my participants or their social desirable responding. So, and those might have some relationship with perceived stress that's nothing to do with my predictors. So what we do is we statistically control for those variables in like a step 1 or a model 1 and model out the variation due to age and social desirability, and then run a model with all of the variables to be able to see how much incremental variance is explained with the predictors that I'm really interested in, which are the total mastery and perceived control of internal states. So it starts getting a little more complicated here because we're doing multiple models. Again, we're still looking at total perceived stress, but now we're going to control for a couple of variables like personal characteristics before we see what is still the impact of mastery and perceived control of internal. So we're going to set up these two models. In model 1, we want the linear model of total perceived stress predicted by age and social desirability. And the data set is survey.sav. So that's going to be mod 1. And then we can take a look at it, right? Give me a summary of mod 1. We can see the impact of age and the impact of social desirability. And in that, social desirability is a predictor of total perceived stress. We can even get the betas for it. So lots of information, the standardized beta, the regular unstandardized regression coefficient, and all of that information. So just like a linear model that we ran before. But now in mod 2, we're going to add some more. So I'm just going to copy this guy from up here right to there. But instead of just age and T Marlowe, I also want T Mast and T Picoas. So now I have my mod 1 and mod 2, and again I can pull all this information for mod 2. I just got to change this to mod 2 beta, this to mod 2, summary of mod 2. So all I did was copy my script and make sure that I've changed the things I need to change. Cool. And we're more interested in mod 2, in the full model. So I can get my confidence interval for R squared on that one. My R squared was 0.47. Predictors now, I have 4 predictors. I have age, social desirability, mastery, and total perceived control. And my N is still the whole group, the 423. So now I have a set of confidence interval for R squared from 39 to 53. Cool. So all of that is kind of what we've already done before, right? We can look at the mod 2. So this one's mod 2. I can look at the F-stat, that it's 9267, degrees of freedom 4418. It's a significant model. We have a R squared of 0.47, and with all of them in here, here are my information for the coefficients, the unstandardized, the standardized, and the significance level for each of those. So all good there, but we're still missing some information, right? When we're looking at a hierarchical regression and those two models, we're asking, does model 2 give a significant change in the ability to predict the outcome? And that prediction of the outcome is seen in that effect size of the model, the R squared. So we went from what? An R squared of, summary mod 1, we went from an R square of 5.9%, so 0.59, right, to an R square of 470. So we know it's a jump. We know 0.58 is smaller than 470, but is it a significant difference? That's the information we need to get from our partial F-test. So we're missing a couple of information we need for the hierarchical regression. One is that change in R square. And like we did, we looked at the R square of model 1 and the R square of model 2. To be able to look at the change, you can just grab a calculator and subtract them. It's really that easy. But if you want to play with coding and put it into R, you can use RStudio or R like a calculator. It would look something like this, where I'm going to give something a new name called RS1, it's just the name I gave it, and it's being assigned by, if we go into the summary of mod 1, I want the variable that is R squared for mod 1. So I'm assigning a value here. And we saw that that is the value of R squared in mod 1, right there. So it took that value from the mod 1 summary and assigned it as an item in our environment with the new name RS1. Cool. We're going to do the same thing for the R squared for the mod 2. Make a new thing in the environment called RS2. It's assigned by the variable R squared in this summary of mod 2 object in the environment. So running that, RS1 and RS2. Now we just tell R to do the subtraction. I'm making a new thing in the environment. I'm going to call it RS change, and it's assigned by RS2 minus RS1. So there we go. That's my change in the R squared. It's the change in R squared. And change, you'll see it as a delta symbol. So my delta R squared is 411. So I could have done that with a calculator probably faster. But once I write this, I could just get those 3 command lines and just put them together and be able to run it. As long as I'm naming my models mod 1 and mod 2, it's going to work for any linear model. So that's kind of handy. Now we still need that partial F-test between the two models. What is the F-test between model 1 and model 2? And for that, we're using a function called ANOVA. We're going to compare mod 1 and mod 2. Pretty straightforward, yeah? So let's take a look at what this does. In here, we have our ANOVA table. Mod 1 was the one with just age and social desirability, and mod 2 had all of them, right? So they went from 420 to 418. So our degrees of freedom is going to be, I think it's 418. I'll have to look at it again. We take that the degrees of freedom is 418 and we added 2 more predictors is what's going on there. So what is the f-test value for like our partial f-test? You're getting most of your information right from this line. Here's our f-test estimate. It was significant because it's less than p less than 0.001, and our degrees of freedom are 2 and 418. So that's the stuff you're picking out of that line for your partial f-test. The only other thing on your partial f-test line is the change in R squared, which we already figured out right there, the 0.411. Whew, lots of information, right? Let's take a look at this in the write-up before we move on to assumption checks. Okay, so our hierarchical regression is written right up in here. We have age and social desirability were entered in step 1. There's our R squared turned into a percent. 5.9% of the variation in perceived stress was explained by this step 1 of the model, which is age and social desirability. Then we entered our predictors of interest, total mastery and perceived control at step 2, and the total variance explained in the model was 47% because it was that 0.470. Then we have our F line for model 2. So the 418, that's 4 predictors, degrees of freedom 418, and the F line that we got from model 2. And the R squared we got from model 2, and the CI from model 2. Interpretation specifically, the 2 measures explained an additional 41.1% of the variation in stress after controlling for age and social desirable responding. And then here's our partial f-test, F2418, our estimate of the f-test, the partial f-test, and it was significant, and then that's where you see the delta. The change in R squared was 0.411. So in that final model, model 2, only the 2 focal predictors were statistically significant. Let's look at it again. So in our mod 2, I'll just call it up again. It's easy to just say, hey, give me another summary of mod 2. When we look at this, only these 2, T-mast and T-PCOS, were significant. Remember on mod 1, social desirability was significant, but once you put in these main predictors, it no longer, T. Marlowe no longer explained a significant amount of variance in the outcome. It was more explained by mastery and total perception of control of internal states. So those are the only significant predictors in the model. The intercept being significant, all that means is that it's significantly different than 0, which is like, yeah, got that. We got that 51.71592 is significantly different than 0. So it's not really very interesting. But it does tell us where total perceived stress would be if all of these other predictors were zeroed out. Like if we had 0 age, 0 social desirability, 0 total mastery, and 0 total perceived control of internal states, then the average stress would be at 51.72. Okay, going back to our write-up here real quick. So there's our information for the coefficients, and we would use the unstandardized coefficient to explain for 1 unit change in this predicts how much change in the outcome. But when we're comparing between the predictors in one model, you use the standardized coefficient, the beta. And then our prediction equation, again, right from that last model 2, 5172, right there, minus age, because age is negative, negative 0.2, minus T Marlowe, it's going to be negative 1.5, minus T Mast, negative 6.3, and minus T Picoas, negative 1.6. And like I said, there are slight differences. See, 1.5, 6.3, all of these came out the same as what we got in SPSS when we're rounding to 2 decimal places. So cool there. Now let's go back and really check out these model level assumptions on the hierarchical regression. And for this, we're interested in that final model, model 2. Again, multicollinearity, we're just saying, are there significant correlations between the predictors? And for this, since we have 4 predictors, it might be easy to make a subset with just those 4 predictors in it so that we can make a quick little correlation table. So again, now I can copy from prior scripts, like when we made a correlation table before, or we did a select before. I'm saying, okay, I'm going to make a new thing, just a subset of survey 2, take dataset survey 2, then select only age, T Marlowe, T Mast, and T Picoas. Cool. Then I can run my correlation run a correlation table between those 4 on survey 2 sub, the thing we just made. So survey 2 sub, and then correlate. And now I can just look at these correlations, remembering I'm looking at multicollinearity. So I'm concerned with any correlation that's greater than 0.9. I don't really care if they're significant or not. I'm just looking at, is anything over 0.9? So looking at these, the highest correlation is between T Mast and T Picoas at 0.53. So I'm not worried about multicollinearity. And I can tell the reader that in that write-up that comes before our results information, we checked for multicollinearity. Doesn't look like a problem there because nothing's correlated above a 0.53. So, and before when I ran it was like 5.2, but 5.3. So no problem there. We do need to request those regression diagnostics for the final model, just like we did before with the augment function. So I'm going to create a new thing in the environment. I'm going to use augment, once I can spell it, of the model, model 2. So running that, and then I want a summary of it. On to regdag, there we go. And then I have all of that information, right? And the same things I did before, I can check out. Like I can go ahead and view it. We can type view, or we can just click it and it pulls it up in our table view. And I can sort Cooksty. That's the little teeny tiny one at 8 zeros before you get to the numbers. And then the largest Cooksty is 0.0587, definitely less than our 1 cutoff. So not worried there. We also have, it just creates for us automatically the standardized residual. And one of the ways we look at outliers is, are the residuals more than 3 standard deviations away from what we expected them to be? And when we sort on standard residuals, the tiniest, so the smallest standard residual, or it's not really small, it's -3 standard deviations. So this is more than 3 standard deviations away from the middle. It's 3.49 away. So that's one that might be a outlier, but we see that its Cook's D is not even near the cutoff. So you can go either way with that. You can say, hey, I identified a outlier with more than 3 standard deviations in the residuals, even though the Cook's D was not near the cutoff of 1. Or you can spin it the other way. A potential outlier was identified due to standard residuals being more than 3 standard deviations away. However, Cook's D did not get close to the 1 cutoff, so we're not going to worry about it. Either way, you just let your reader know what you're doing. Typically, if you're going to keep something and you're considering an outlier, you would possibly run the regression twice. You run the regression with that case, or those cases if you have multiple outliers. Run the regression retaining the outliers, and run it again without the outliers, and that way you see if your results are substantially different. If you're coming out with the same results anyway, there's no need to delete data or to not use data. But if you're seeing that the the outliers are making a change in the results, now you got a bigger issue, because you need to say, okay, why and which results are most valid. And that starts getting quite a conversation. Okay, so that's outliers. We have those normality and linearity and homoscedasticity of the residuals. And again, this goes back to normality, histogram and Shapiro-Wilks, linearity, scatter plot, and correlation test, right? So I can go back up to where I did this for the prior model. Right here, I have normality of residuals and the linearity, and I can just, I'm going to copy all of it and then take out my extra writing. Right here, paste. I'm going to take out all this extra writing. Leave myself some comments so I know what I'm doing. So this one was assumption. And now I need to change these things. I don't want MR1 regdag. I want the mod2 regdag. Once I have it there, I can just copy, because all of these are the same. Resid is the same, fitted is the same. The only thing different is the item in the environment that I'm asking R to work with. I wanted to work with Model 2 regression diagnostics, which I already made before, right? So just changing out all of these, and now it's ready. So you don't have to write from scratch each time. You can use your script that you've already been using. So there's my normality histogram. Here's my Shapiro's test. Pretty close. It's still significantly violating Shapiro-Wilks. And again, we know that Shapiro-Wilks is a little sensitive to high sample size, and we still have like over 400 sample. That's pretty close. You would let your reader know what you think of the visual inspection of the histogram and report the significance value of your normality test. Linearity, we got our scatter plot between the residuals and the predicted, giving a look at it. Do I see a positive or negative trend in this relationship? Do the correlation test. We have very much zero there with 15 zeros. So it's a negative, lots of zeros, 7556052, and p-value 1, not even a significant correlation at all.
So I'm not worried about linearity of residuals. You make your call on the normality. And then homoscedasticity of the residuals is again looking at that same scatter plot, but now we can put a midline by going to that plot of mod 2. And that's where we have to hit return to see each one down in the console. So there's my residuals to fitted with the line in the middle. Here's my QQ plot. How well do those residuals stay on the line? There's another fitted to residuals plot, very similar to the first one. And then the last one, we're not really doing leverage, so don't worry about that one. Okay, wow, right? Lots. We have the information we need to write up the hierarchical regression. And sometimes you're doing the write-up, like back in here, and you're saying, oh man, what was that correlation, or what was something, you know. So I can just go back up, and if I want the correlation again, I can just rerun the thing. And now I have that. Here we wanted to look at the predictors. Are they highly correlated? We can just rerun it, or if we save it in the environment, we can get the summary again. And like I said, as you're doing these things, these assumption checks, you might just start writing it in. You can start with like bullet points, like, hey, I checked multicollinearity, and here's what I found. I checked normality, and here's what I found. I checked outliers. And then you can remove your bullet points and craft it more into a paragraph. So see what works best for keeping track of the information you have in the output in the console and getting it into your write-up. Be sure to keep any figures that you like, and we still need to build the table. So let's look at that. I'm going to go over to our starter tables that you downloaded, and you've got a lot of different starter tables here. The one that we're going to be working with is Table Regression 2, which is the one that's set up as a template for hierarchical regression. In this, think about the information you have. We can get the confidence interval for B. All we had to do, just like before, is ask for confident of whichever model. So let's say mod 2. So if I get that, now I have the confidence intervals for all of those unstandardized regression weights. So easy to pick it up if we want it. When I ran it and made the model, made the table during SPSS, I was just using the effect size. So you want to have effect size or confidence interval or both when you're telling your reader about that stats line. Like you give them the estimate, you give them the significance, how significant was it, and you give them either effect size, confidence interval, or both. Some parameters that we're estimating are easier to explain with our effect size, like how strong is each predictor relative to the others, and some information is easier to explain with a confidence interval, kind of like R squared, right? So it depends. I didn't pick them up, so I'm going to go ahead and get rid of these two columns since I'm not going to need them. And I don't really need 2 rows for variable. I don't know why I have that. And then I did not do 3 steps. I only did 2 steps because I put both total mastery and PCOAS in on step 2. So I'm going to change that to step 2, and I'm going to take out this whole middle section. But it might be useful in the homework where you have 3 steps. And again, you would just do mod 1, mod 2, mod 3. Right there. And then all this information I need to go make sure is correct. So I'm going to delete all that. I'm not doing confidence interval. Now you do want to tell your reader what any abbreviations mean. So we might want to add stuff in there. And I'll leave the significance line until I get all of my asterisks in to know which ones need to stay here. But I think I'm ready for moving some information over to this table. So I'm going to rearrange my windows and do that. And I'll speed it up a little bit so that y'all don't have to sit here and watch the whole thing so slowly. Okay, so I tried to keep everything at 2 decimal places, except for the R squared stuff. I went ahead and went 3 places there. For unstandardized regressions, regression weights, they can go above 1, so I need the leading 0 on those. Standard error can go above 1, but betas don't typically go above 1, and R squared doesn't go above 1. So you only need the leading 0 if the value itself can go above 1. It's an APA thing. So let me copy this and see how hard it's going to fight me getting it into Word. So I'll go over to my write-up. I'll just go to a new page just to see how bad it's going to fight me. I'm doing Command or Control Enter to make it jump to a new page there. And typically your tables go before your figures, but here I'm just seeing how hard is it going to be to get it into Word. So I have this much. I can see that the margin's a little too tight there. So I selected the whole table with selecting that little hashtag box in the top corner of the table. You just sneak up on it and select it, and it selects the whole table. In layout, I'm going to go to auto fit window, and that brings it into the margins. This beta being here is problematic. So I'm going to try copying the beta. So I did Command C for copy, and it's like in its own little table here, that little table symbol. So I'm going to delete that little table, and I'm going to turn on non-printing characters with this. I'm on the Home tab, and then this backwards P is a paragraph symbol, and I can see that there's a return there. So I'm going to hit delete. I'm just going to see if this will paste. Can I paste the beta back in? Yeah, that worked. Cool. So I need to center this guy, and it needs to have its top and bottom borders, right? So I'm going to put bottom border and top border. Okay, that's good. What else do I have here that might need cleaning up? I might want to tell the reader which symbols are unstandardized and which symbols are standardized betas. So I can do that by just kind of typing it in, that an italicized B, oh, I'm going to have to write a little bit more, and then tell them what the B is. I'm going to want that a little smaller too. Okay, what do we got? Let's make all of this 10. Let's see what that does. Okay, it got it to the same size as the others. This B needs to be italicized. Need a period there. Okay, and then looking at our p-values on this caption note, the only ones I'm using in here are the three asterisks. So I don't need these other ones because they don't pertain to the table. Alrighty, looking okay. Those two are kind of close together. Let me turn off the non-printing characters because it looks kind of busy when you see all of that going on. This would be table 1. And that would be a pretty decent table. I might screw with it some more to try to get those two columns to not be so close together when I have all this spacing here. But other than that, it's looking pretty solid on its APA. So even when I cross things over from Excel or from output and it says it's going to try to get it into APA, a lot of times I still have to do some finagling to get that to actually work. Let's bring this back over. So we got a lot done here. This is a very involved lab. We're really starting work with our multiple regressions and evaluating model level assumptions. So these are assumptions on top of what we do in the beginning, like our univariate normality and bivariate linearity. Now we're like adding more assumption checks of the model itself, which we can't really do until we run the model because we need the residuals to be able to look at their characteristics. So we ran our multiple regression, but then we also ran a hierarchical regression, which gets a little more complicated, but it's a little more realistic on what we see in our workplaces, organizations, or practices, that we want to statistically control for variables that might be related to the outcome that we had no way of controlling for in the design of the experiment or the evaluation, assessment, whatever. So this is a normal part of being able to look at the impact of our predictors of interest while controlling for things that maybe we didn't have control on because it's just part of normal people, right? So we interpreted the results, kind of got them into the write-up, we pulled the information for our prediction equation, and we created a nice table for organizing those hierarchical modeling results. And that is it for our RStudio lab, and I will see you in the next lab.